Ah, hello. Hello. Total double hello, John. Oh, Lizzie's already laughing. Wow, that's but hello, John. Hello, John. Hello, Lizzie. Hello, Eric. Oh, Eric. Totally. Eric is like the new and hi, May. Hi. Okay. I don't know what I was about to say. Well, I sort of do, but I missed you, Jayla. How did I do that? We've got issues. Hi, Newell. All right. Did I say we have issues? Um, yeah. Oh, you already, wow, you're way ahead of me, Jayla. Okay. Well, we have to, okay. Well, I don't even know if there's enough weeks in the semester left to unpack this Jayla issue, but okay. Yeah. What is this? Okay. So, hello. Wait, do I? Okay. All right. And John, wait. So, oh my God. Guys, I've been in such, this class really like, my ability to teach is so small this week. I'm like hanging on a teaching thread here, and yet this class makes me almost enjoy my life. No, I do enjoy my life, but this class makes me changes my view on everything every time. Now, hold on a second. Okay, wait, I'm getting the chat is running away from me. This business that, yeah, okay, I'm glad. Thank you. All right, I'm gonna get to, okay. Oh my God. All right, I'm gonna say right now, I almost don't even think we should be recording. We should not be recording right now. I'm going to tell you right now that we are going to spend the bulk of class today actually studying and preparing for this exam. That is, we are actually going to be in our individual mental spaces, working with the practice document, the practice exam. That is what will be happening here. I'm going to do a quick confrontation of one of the questions first before I release you. But before that, I'm saying that to keep myself on track, because if I'm not careful, I'm going to dive into the waters of this chat and start doggy paddling like endlessly, if I'm not careful. Like this chat, I mean, there's so much group therapy to work out here before we even get to the physics. It's astounding. I mean, all right. So first of all, and I don't know where to begin. And I mean, any minute now, I know. I mean, just when I finally get calm with this material, and just when we're all about to get A's and know lots of physics, I know what's going to happen. Is like basically is going to come and sneak attack me. Oh, here comes people. I mean, it's the people that I think are not insane that are going to turn out to be the true like mystery Mario axe wielding antagonist. I don't know what I'm saying. All right. So what I'm saying is, first of all, wait, what? Okay, wait. All right, I'm looking in the chat. All right, wait. I am going to deal with this chat, but first of all, I am glad. I'm just going to say, for the first time in 2 semesters, I am glad that Maisha has conceded to John, for at least for today. I mean, I don't think it's a permanent concession, but I'm glad that at least for today, Maisha has conceded to John. And I mean conceded, CONCEDED, not CO. I'm not saying she's arrogant. I'm saying I'm glad she has made a concession that at least today, John is the winner of that particularly weird ongoing competition of because yes, apparently Maisha has a meeting today, which now I'm going to go public with this. I'm going out on a limb. Like both John and Maisha are telling me that she has a meeting. I don't know what this meeting is that takes precedence over class. I mean, what really, and I don't think I want to know. I mean, I'm not sure what answer would be satisfying to me, but the idea that she even that anyway, all right, whatever. I'm glad that, and I know that John was in the waiting room for like since 1967, and then I'm getting texts from Maisha about like that she actually even said hi in a text, and I thought, is she actually going to claim firsthood for this class when she's not even showing up? But no, all right, at least she told John. All right, anyway, so there's that. But then there's Jayla and her name pronunciation. Like, I I'm going to have to meet you in person. I'm going to have to get, I mean, I hope it's true because I really feel like there's something going on here with my pronunciation of your name, and I'll never know until I actually deal with this in person, but I don't know. All right, I'm reading the chat again, but I don't know. Yeah, I'm all sketched out. Okay. Oh, I never even said hello to people. I'm sorry. Wait a minute. Okay. Hello, John. Hello, Eric. Hello, Jayla. Hi, May. Oh, I did say hi to some people. Hi, Noel. I did. Okay. But yes, hello, Jayla. Right. Oh, but it stopped at Elizabeth. Hello, Elizabeth. Thank you for putting up with your colleagues and with me. Sorry. Jayla. All right. I'm going to believe you, but I don't know. Okay. And hi. Hello, Lizzie. I never said, I did say hello to the visual Lizzie, but not to the name Lizzie. Okay. Hi, John. Okay. John. Okay. That's funny. Wait. Lizzie's been spelling John's name wrong. How do you spell John? Oh yeah, I guess she has. Oh yeah. Sorry. Okay. Well, yeah. So, okay. Okay. But May, she's not here. Yes. Don't worry about that private chat person. Okay. Good. Oh, all right, Jill. Okay. But then why? Okay, cool. I'll accept that, Jayla. Thank you. But okay, now funny. Wait a minute. All right. So I guess we do have to get to material here. And sorry, I'm a little bit off. I know I've been off this whole week. I mean, off, like off. Okay, I want to get straight. What we're mainly doing today is we're going to start preparing for this exam. As I've mentioned before to those of you who've had me, I mean, the best way to prepare for this exam, which will be posted a week from tomorrow. So we still have 2 more classes next week to answer questions and stuff like that about it. The exam will look very, very much like the most recent, oh my God, I cannot speak. I'm going to continue to put updates to this practice exam. Like the bottom line is that the practice exam is like a draft for the exam. And as I improve it, or as I find errors, or as I find things that are more appropriate to your class, then I make those changes and then I post those changes to you. So by the time we get to the actual exam, it'll resemble quite remarkably whatever the practice exam is looking like at that point. It won't be identical, but it'll be super, super close. You will have a bunch of answers by then, or solutions. Anything that I don't give you solutions to by then probably means that if there's a question that I haven't given you a solution to by the time of the actual exam, it probably means that that exact question will appear in that exact form on the exact exam. Like, and that's probably maybe either why I didn't give a solution to it or because I didn't give a solution to it. But then other things where you get solutions to them, then that means, I reserve the right to vary the details slightly for the actual exam. So the best way you can study for sure, of course, is to just work with this practice exam intensely. And the best way you can work with the practice exam, I mean, I've given big speeches about this in the past, and if I'm not careful, I'll accidentally give a big speech about it now. The best way is just to try to do stuff without looking, obviously. And then when you run into trouble, then look somewhere and try to get help, and then try to do it, and then try to do it again without looking. Like, you really want to be able to do this practice exam with full confidence. The more you can work with each other at every point from here until then, the better. So there's going to be time today, if I ever shut up, when I shut up, there will be time where I'm going to really ask and really strongly urge you to work with each other during the Zoom to help each other on this practice thing. But it's all about the practice exam. So one thing I want to do first, and this sort of answers this is it partly to address John's question in the chat. I first want to address one particular question in the practice exam, a particular question that is exactly where we left off going over homework 2. Like John's asking in the chat, are we going to continue going over homework 2? the most efficient way that I can try to balance all of our considerations right now is if I direct your attention to a certain question in the practice exam that is exactly from homework 2, and it's exactly from the last place we were in homework 2, I think that would be the fastest way to get us straightened out with this material. So what I'm saying, and also, okay, so what I'm saying is please open your practice exams. I'm saying please have your practice exams out in front of you, and please turn to part 2, just for the moment, for the moment, turn to Roman numeral 2, part B. I could screen share in a minute. Yeah, I guess I'll screen share if I can. Yeah, I'll screen share for a second. Yeah, please turn to this page 5 of the exam, I guess it is. Okay, and I'm going to say, like, I think this is a good, this is a question on the exam. Your question on your real exam will look very much like this. I personally think it's very fair. I mean, whatever that means, but it may look intimidating, but it is very, very much like what we've been doing for all these weeks. Sorry. It looks intimidating, but largely it looks, I'll just say right away, largely it looks intimidating because the constants have intentionally been made to look very detailed. But like that whole thing in the parentheses, right? Okay, so I'm speaking in overview terms right now. If you look at part A, it says assume the differential equation, blah, and then show why, blah, 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 blah. If you look at that differential equation, what I want to tell you right now is that is an example of the differential equation for simple harmonic oscillation. And by the time you're taking this exam, you should recognize that. I shouldn't say should, but it is expected that you recognize that that thing is describing an X that is harmonically oscillating in time. Now, the thing in the parentheses may look intimidating. You might at first look and say, wait, we've never seen anything with a Q in it or like a capital R or whatever, but they're all constants, right? It says that K is a constant, Q is a constant, R is a constant. So that means that entire thing in the parentheses is a constant. We're trying to get ourselves to the point of realizing that if that whole thing is a constant, then it's a constant, and we don't care how ornate or how detailed or how unfamiliar the letters are. So we have an equation regarding X where the second time derivative of X is equal to a negative times a constant times X. That is the first differential equation of this course. Like that is the differential equation for harmonic oscillation. We want to be aware of that at this point. So now we get to part, well, I'm going to switch boards in a minute, I'll switch screens, but I'm just walking you through here and again, what I'm walking you through here is the practice exam. So it's meant to help you with the actual exam, but also, to be honest, to address John's question, like this basically is what's going on in that homework 2. Like homework 2 is good practice for this as well. And this is pretty much right where we left off going over homework 2. I mean, this type of material. So it says, show why the following trigonometric expression is or is not a solution. Does the cosine expression satisfy the differential equation? All right, I'm gonna tell you. I'm going to tell you right now that the answer is going to be yes. Okay, I mean the correct answer to this will be yes. The way, and I'm not going to walk you through this one. I'm going to walk you through the next one, but they're totally identical. But you should do this one yourself for practice. If you do this, you will find that the answer is yes. And how do you do it? Like, what does it mean to do? How do you answer question 2 where it says why, how, or why not? You take 2 derivatives of this. Okay, that's what you were practicing in homework 2. Again, I'll show you that in a minute, I think, in the next piece. But I want to leave it to you to practice. You show as much work as possible, and you be as clear as possible, and you do the 5-step method possible, and you show colors or diagrams, whatever. But what you really need to do is take a derivative with respect to time of this expression, like take dx dt of it, and then you need to do that again right? You're going to take a second derivative, and then you're going to see if upon taking two derivatives of this carefully, do you get back the original expression itself times that constant up there times a negative sign, okay? Now you're going to find if you do this correctly that you do. I'm going to leave that to you right now, or not right now, but like in 20 minutes to do. But the answer, you'll know you did it right if your answer is yes for 2A11. And then for 2, when it says why or how or why not, you're good. That's where you show, like, because you'll say because the second derivative of this expression yields this expression times KQ over R cubed times a negative sign. Okay, so the how or the why is taking the derivatives. And you definitely could take the derivatives first to figure it out, and then you can, in question 2, say C above C2 derivatives or something like that. But that's, anyway, I'm just looking at the chat. Oh, wait, great question. Hang on a second. John Ford's question in the chat. Which one is time, KQR? No. I mean, great question, but none of them is time. Time is T. Like, time is the lowercase t that's in the denominator of d2x dt squared. And also it's the t that's like next to the whole parenthesis in the brackets in the cosine expression. Oh, wait, let me look in the chat again. Maybe, wait, sorry, I'm looking at, oh, okay. Yeah, so, but that's important. I'm glad he's read so good. And that class participation points, everything, please. But yeah. And so to everybody, that's not a stupid question, because it's super important when you're taking these derivatives. Yeah, you want to know what the independent variable is. It is t. And you definitely want to treat everything else that's in there as a constant. Okay, now I'm going to show you, and stop me if, I mean, please, those were good questions. Anybody or everybody stop me if you have more. But what I'm going to do now is I'm going to go on to the next one, okay? That one I just gave you an overview to guide you in your practice today or in the future. But then number 2, I'm going to talk a little bit more now. 2 is the same thing. Wait. Yeah, I mean, like little Roman numeral 2. I'm going to switch screens in a second, but little Roman numeral 2. Now we're asking, is this E function a solution? Now this happens in homework too. We just didn't get to talking about it yet, but we're asking the same question again. We're asking, is this thing a solution to the above differential equation? Is it a solution? Meaning, does it solve it? Meaning, if we take two derivatives of this thing with respect to t, will it yield the condition that the differential equation up there says? Now, let's be clear. First of all, this is a very intimidating expression for sure. I mean, it looks very complicated. Also, it looks new. Like we've been dealing with cosines for like a month and a half. We're getting very used to cosines. And if you've been paying attention, you hopefully are sort of getting used to the idea that we've been treating the cosine solution as a solution to the differential equation. But what's also really important to know is, first of all, we never said that our cosine solution was the only one. We said that it was one. We've been using cosine because it does work. We didn't say it's the only thing that works. And now let me go a step further. That sounds like just an obnoxious technicality, perhaps, to like suddenly arise right before the exam. But no, it's actually, it may be obnoxious, but it's not a technicality. Meaning, remember, for like the first few weeks of the course, we were saying, okay, to solve Hooke's law, we have like x equals x naught cosine omega t. Like that's like cosine omega t, we were saying for a few weeks and doing stuff with it and taking derivatives and blah, blah. Then we hit this point in the course where one day in the middle of homework 2, actually, and in the middle of lab 3, we said, hey, wait a second. What if it's cosine omega t plus phi? Like we asked, wait, what if we put another number into the parentheses, into the argument of cosine? Does that also work? And it turns out it did. So we found out later in the course, oh, cosine omega t is not the, or cosine omega t plus 0 is a solution, but it's not the only solution, or it's not the most general solution. It's not the solution, it's a solution, we found out. And that was an important thing to find out, because then once we could make it more general and add a phi there, we were able to have multiple oscillators and make waves and all this kind of stuff. So we did all these things once we realized that our cosine was a good solution, but not the only one. Well, take it even another step further. Once you're allowing for a phase constant in the cosine expression, once you're allowing for a phase constant in the cosine expression, once you're allowing yourself to shift the cosine graph like horizontally along the t-axis, then if you make the phase constant pi over 2, 90 degrees, that's equivalent to changing your cosine to sine. In other words, some of you that at the beginning of the course might have been thinking or saying, wait, is cosine the only function that when we differentiate it twice, we get back itself with a negative sign? Like, doesn't sine also work? I'm saying, oh, yes, you're absolutely right. We've been deliberately using cosine because it has certain conveniences, because we like the fact that cosine starts with a y-intercept rather than at the origin. And it makes it easier for us to use cosine if we don't, then we can set the phase constant to 0 and stuff like that. But it's just easier than sine. It's not more correct than sine. It raises the point that there's either lots of different functions, perhaps, that could satisfy this differential equation, or put another way, there's lots of different ways to write a cosine that all ultimately mean cosine. Like you could write it as cosine, or you could write it as sine of theta plus pi over 2 or something like that. So when we now get to this question here, all of a sudden, we're now dealing with E functions, not cosines, not sines, but E. It's totally possible, for all we know, that E is going to work also. I don't know until I try, but the question here is, does E... Okay, I'm going to look at, I see John's question in the chat. I'm going to answer in 1 second, but, and sorry, I know I'm talking for way too long here, but we're in a minute. I'm going to do, or like in 30 seconds, no, in a minute, I'm going to do the question that's facing you on the screen with the x equals x naught E. It looks all complicated, but what it's a way of saying, now that we've established that cosine functions work and more than one cosine function works, now that we've established that even sine functions work too, like, are there other functions that might work as well that might satisfy this differential equation? And the question is E one of them? And so that's what I'm going to try in a second. But John says, is it because the constant cancels? I think that's a really good question, but I'm not sure. Is what because? Oh, very good. Oh, yeah. When you do a phase shift, the fact that the constant has a derivative of 0, the fact that the phase shift, the constant, it's not so much that it cancels exactly, but that, oh, okay, yeah. So yeah, then the answer is yes. Cool. I mean, good question. Right. So that just goes to show, like John's questions in the chat, and then my larger point goes to show, we're trying to solve this differential equation. What that means to a physicist is, this differential equation, please remember again, is a way of saying Hooke's law. The differential equation is a mathematical way of saying Hooke's law is applying here. But we want a function. We want a way of relating position to time, or whatever the dependent variable is, to time. We're looking for a function that takes time as its input and spits out the dependent variable as its output. We're looking for functions that actually satisfy Hooke's law, but allow us to predict what the value will be of the dependent variable at any given time. So the question before us now is, okay, we've established that cosines work and fancy cosines work, and therefore even sines work. Does E work? Can we use E to describe the motion of a simple harmonic oscillator? So I'm going to switch boards now and do it. So this is okay. So I'm gonna tell you right now that I think the answer is going to be yes, but here's what we do in order to find out, in order to know. Okay, what we need to do, I'm just switching my thing. What we need to do is compute derivatives. And this is what we were practicing all in homework one, well, in homework two, I guess, all the beginning of homework two. We're going to take the derivatives of this expression, derivatives with respect to time, and we're going to see if the second derivative does what it's supposed to do. Okay, so I'm going to, I wish I had written this on the next, all right, I'm just going to recopy it one more time. All right, so here we're going to take a derivative. So I'm going to do what I always do. I'm going to assume I know trigonometric derivatives, like I know that the derivative of cosine is negative sine, and I know that we've got a function within a function here, a function of a function. So I know I've got to use chain rule, right? Should I drag this in? Well, you'll tell me if you want it to see the extra step. I'm saying this. Right, that's the first derivative. Tell me now. I probably haven't said anything of value this entire class yet. That's probably the first thing I've said of value. So look at it, please, and make sure you agree. Really, really, anybody who's tuning in and out, like, make sure you agree. That's, I mean, I haven't proven anything, I haven't finished anything, but that's the first derivative. I think that is the first derivative. And again, I think even though that expression upstairs looks very complicated, it is a real expression, just so you know, too. It's not just gibberish. Like, I didn't just make it up just to be annoying. Like, it all does signify something, but no matter how complicated it looks, just realize that everything before the t is one big constant, and everything after, like everything in that parentheses, and everything that is being added to t is one big constant. So I should also say here, I'm even here, I'm doing steps in my head that I probably shouldn't. And when you turn in the exam, I think you should even add more steps than this. Like I'm doing the chain rule, and you should probably spell that out. And I'm doing trigonometric derivatives. I should probably be spelling that out, but I'm getting myself in a verbal jam, so I'm just not. But okay, yeah. I mean, right. So this is definitely the chain rule, and you definitely want to show it, but. Like what I'm really trying to say right now is I'm trying to help you guys get the answers here right now. I'm just trying to make sure you get how to get this. Is not a formal solution that I'm doing. Like, don't just copy this and then and say, well, this is what you did, so I should get 100 points. Like, this is just me sketching out the main points right now. But so I take another derivative. So now it's going to be right. In other words, what happened there? The square root of KQ over R cubed, that constant came out again. So it's got squared at the front. I really should be explaining this if this were an exam. I mean, I'm explaining it verbally. You should explain it on paper. I'm saying that this came out again. So it was a square root squared by the end. So the square root went away, right? And the sign turned to cosine, but the negative sign stayed there, right? So then I'm saying, well, here, I'll go one more step. So now I'm saying, I'm going to look in the chat. I'm just going to look in the chat for a second. Oh, yeah. Okay. Oh, can I go back? I'm sorry, Lizzie. I totally missed. Go back. Yeah, I'm sorry. To this? Sorry, I totally missed. I'm really. Okay, no problem. Thank you. And that totally counts. Okay, cool. So there's that. Okay. So now here's my big point for right now. Even though this whole function looked complicated and all of that, wait, what am I doing? Am I doing the right question? I don't even know what question I'm doing. Wait, what question am I doing? Hold on, sorry. Oh, yeah. Oh, wait, but this is not what I meant. Oh, this is the whole thing that I just said to you guys. I was just explaining and I wasn't going to do. But all right, I guess I'm doing it. I'm sorry. Oh my God, I'm really losing my. This is all. I meant to do the next one, but okay. This is right. This is right. And this is what you do. But I meant to have you do this on your own. But okay. Hold on. Let me just make sure I'm doing the right. Oh my God. Right. So this is all. This is all. Okay, so look, and please stop me if you don't know where I am. I mean, I'm just going down page 5 here. I meant to not do all of page 5, but apparently I am. So this is technical, but hopefully you agree that this is practice, what I'm doing right now. I mean, you've seen this before. It looks all complicated, but you've totally seen it before. So what I'm ultimately saying is, okay, look, and this is the, oh God, sorry, this is totally what John pointed out before. Like, this is where the constant pi squared over 9, like was sitting there and looking annoying and looking intimidating because it's like pi squared over 9, but it goes away. This is the thing that John was saying. It doesn't come out when we apply the chain rule. So it doesn't mess up the derivative. So in the end of the day, what I'm saying is, at the end of this day, I'm saying like, right, I'm going to flip the pages back and forth quickly for a second. Like I'm saying, look right here. We took two derivatives of, we started with an x. This is our expression for x. We started with an expression for x. We took two derivatives of it. So we got the expression for the second derivative of x with respect to t. But this long expression that we got for it had all this stuff in it. But if we were wise, we noticed that all this stuff that was in that expression was just the original x. Like that's the big point, that we took two derivatives of x and we got back to x, but then times a constant times a negative sign, and indeed times the exact constant that we wanted. Like the whole question was, if we take an x, and the whole question was, if we take two derivatives of x, will we get back x times a constant times a negative sign? And we did, right? So our answer is yes. Oh, God. Okay. So we proved yes. So that cosine expression could be used as an equation of motion. That cosine expression we could use as a rule now to apply whenever you want to. You name the time, I could tell you exactly where this oscillator would be. Like if you plug into that x equals blah, blah, cosine, blah, blah expression, it will work for this x that is evidently going back and forth on a spring according to the differential equation that was provided. All right, so that would be the answer to that one. That's review. Now, when we go to the next one, if we now go to little Roman numeral 2. Okay, now this, so we're going to do the same thing again here. We're going to do the same thing again, but this now looks intimidating, even maybe more intimidating for two reasons now. One, there's E involved. Have we ever talked about E before in this class? Not yet, no. And two, there's an I involved. I, like, since when is I part of physics? Fair questions. Here's the but it turns out they both are very involved in physics. Both are very involved in physics. What do you need to know about E? What do you need to know about I? What you what you need to know about both of them is exactly what's written at the top of homework 2 and what's written on the first page of the notes of today. Here's what you have to know. Right? The main thing to know about E, perhaps the only thing you need to know about E, the essential thing about E, is that e to the x is its own derivative. That's the key thing about E, that the e to the x function is literally its own derivative. If you have a function y equals e to the x, then the derivative dy dx is e to the x. That's a powerful statement. It's the essence of E, that it is the function for which the rate of change of that function, or the rate at which that function changes, is that function. So we're going to use that when we take the derivative here. We're also still going to use chain rule. So we're going to do the same thing we did a minute ago. Instead of just doing like sine, cosine derivatives in chain rule, we're going to do e to the x derivatives and do chain rule. But then the other thing is, what's the deal with this I? So next page, what's like, how do we handle I? I, you may have heard, is called an imaginary number, and that's, I'm not sure if that's a good word for it or not, but I'm not sure if that makes it seem more exciting or more confusing. But I will tell you this: what I is a number. It is a number. It is always the same number. It is therefore a constant. And that's all that we need to care about or know from the standpoint of taking derivatives and all of that, that I is not a variable. It is a constant. It is a number. And the number that it is literally the square root of -1. The fact that it's the square root of -1 is literally all we need to know to do any of this stuff, as long as we know how square roots work and how the number and how negatives work. So watch, we will, with those two facts, we are totally capable of taking any kind of derivatives of any kind of e's or i's, no matter how complicated they look. So we're now going to do this question. Okay, so I'm going to compute the derivatives. Okay, I'm trying to go slow. Okay, the first thing I'm saying somewhat illegibly is, so I'm trying to take derivatives, right? I took the first derivative. What I'm doing is I'm saying the derivative of e to the blah is e to the blah, right? So in the original expression, I had e to this whole big blah thing. So I basically just copied that again, like in my derivative, e to the I blah, 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 t blah, blah, plus pi squared, blah, all of that comes down, is repeated, like verbatim, because e to the whatever, if y equals e to the whatever, then the derivative is e to whatever. But then there's chain rule as well, because it's not just e to the t here, it's e to the some function of t. So I've got to multiply, and I can break this down. I can give another example in a second if anybody wants. If anybody has the guts to ask in the chat, like, wait, I don't get how the chain rule works here, I can do a side example that will break it down. I'm happy to do that if anybody wants to ask. But I won't do it if you don't. But so you see, I took everything before the t, I took out and multiplied the entire e expression by, just like I did before, right? It's just like what we did with the cosine thing a minute ago, a page ago, that whatever was inside the argument came out and multiplied because of chain rule. But the pi squared over 9 does not come out because that's a constant, like that's John Ford's point, right? So but just notice, in other words, I didn't do any, the number I didn't do anything weird or special or interesting to our procedure. I just treated it like it might as well have been the letter B. It's just a number that came out along with the square root of KQ over R cubed, right? So so that's my first derivative. Okay. So now I go to my second derivative. And the exact same thing is going to happen again, just like before. Like we're going to have to do chain rule again. So we're going to do, so again, we have the derivative of e to the whatever is just e to the whatever. But so the only interesting issue here is the chain rule. So we're going to do the chain rule again. So whatever is in the brackets in the argument of the exponential is going to come out again. So they're going to get squared, right? So now it's going to be I squared times KQ over R cubed X naught. The X naught does not get squared, right? Because that was already there. That's not part of the bracket. Right? Is everybody with me here? So it's just like the cosines and the sines. It's nothing new. It's nothing interesting. You just have to know that the derivative of E is E. So we have this now, but now we're almost there. But now notice this. Oh, very good. Thank you. Like, yeah, good question, Lizzie. Like my handwriting is terrible. I'll try to recopy it more clearly on the next page. But yes, like everything that's, and it also helps if you look at the actual exam sheet, it might be a little bit like better to look at than my handwriting, but everything in the brackets E is being raised. Yes, E is being raised to the power of everything that I tried to write after it. It's E to the all of that. Whatever's before E is just being multiplied by that. So I'll try to write it more clearly on the next page, but I don't know if that answers, but yes, that's E to the all of that crap. Let me try to write that one more time and see if it. Like, I don't know if that makes it, or Lizzie, can you just tell me, am I making it more clear now or less clear? Like, yeah, it's E to the all of that is, maybe you could tell me if I'm answering here. I mean, it's E raised to the that. Is that? Yeah, okay. Thank you. Okay. Whew. Okay, because now here's the big, huge leap, everybody. Like we're almost done. Oh, and I'm forgetting. Whoop, I dropped off an X naught. I think X naught dropped out of it. Sorry. Hold on. Okay. Now we're almost somewhere here. But now, well, check this out. I mean, just like before, one thing we can notice is that this, right, this is all X again, just like before, not a coincidence. Like X came back. Now it's not a coincidence because that's the whole point of the e to the X function, that when you take the derivative of it, you get back itself. So then you take a derivative of it again, you get it back itself again. So we did get back the original X, and it's being multiplied by a constant, but then it's being multiplied by I squared. So what's the deal with that? Good question, John Ford. But it's not, well, because, okay, it's not just the X naught E that's translating, it's X naught times E to that whole thing. And the reason that translates is because, look, like it is right here. This is what, like, X is. And did I drop? I might have dropped. Did I drop out the pi? Hold on. Did I drop out the pi square by accident? Hold on. No, I didn't. No, I didn't. Right. So look, X. I mean, this. Oh, okay. But that's a really important question that John Ford is asking right now. Like, it's so not a stupid question, seriously, because it is the thing that's the hardest to see for everybody always in these exams. Like. It seems like a sneak attack every time. It almost seems too good to be true or something. But yeah, X in the first place was defined to be that function. Like that's what we're trying. We're trying that complicated function for X to see if it actually does what we want it to do. And what is it that we want it to do? We want it to spit back itself times a constant times a negative sign after we differentiate it twice. Like that's the whole test here, is whether we're picking different functions to see whether after we differentiate them literally specifically twice, whether we get back themselves, but times some positive constant times a negative sign, right? And it appears weirdly, no matter how complicated this thing is, and see, notice we're picking functions that have a chance of doing that. The reason we're playing so much with cosine, sine, and now E, like where did E come into our lives suddenly? Like totally, if I were in the class, I mean, believe me, if I were a student, and when I was a student, if all of a sudden E just popped up in all of this, like I thought we were talking about physics. I thought we were talking about a mass going back and forth on the spring, blah, blah, blah. Like when did E suddenly come into it? E came into it because we're trying to think of mathematical functions, mathematical behaviors that actually have a shot of producing feedback. This whole thing is about feedback. Like a differential equation is necessarily some kind of feedback. What do I mean? Now, I don't want to get myself all on a tangent here, but what do I mean when I say feedback? I mean, remember, the rate of change of X with respect to T is apparently some function of X. That's in English. Remember, we're saying we want to know where the mass on the spring is at any given time. We want to know what is the position. What we spent all of physics 203 learning, and no joke with this, what I'm about to say. Oh, yeah. Wait, so I'm going to go back. Oh, wait. Oh, great. Okay, sorry. I'm gonna stop the babbling fest, and I'll just like bring this. Let me just finish the thing I was saying before. But what Jayla has and what John have in the chat is totally relevant. Like it's like totally the point. That's awesome. Even though Jayla keeps mispronouncing John's name. No, just kidding. Yeah, no, I totally want to get to what Jayla and John have in the chat. Let me just finish this stupid point that I'm making that I think actually maybe people understand. But just please remember the whole why this keeps happening is we have this mass on a spring. It's going back and forth. We want to know the basic physics thing of if you name the time, can I name the position? Like, right? That's the essential physics question. What you spent most of physics 203 learning, make no mistake, what the point of most of physics 203 is really to drive home the idea that whenever in life we want to know position, it's generally super helpful to know acceleration. The whole point of physics 3 is we can get position if we know acceleration. And that's true, like that's right. And that's physics 203. What this problem, the beginning of 204 says is, oh, you want to know acceleration? You want to know the acceleration of this mass on the spring? Well, no worries. The acceleration just totally depends on position. That's a loop. We're literally saying the rate of change of position with respect to time depends on position. That d2x over dt squared equals blah, blah, blah. X means that. It means we've got some kind of position, some kind of function of position that when you look at the rate of change of it, you get back itself. We are looking for functions that do that. And e to the x is a function that does that. When you differentiate it, you get back itself. So it's got a chance of describing the situation for us. So now I want to get back to this problem, and I want to get back to what Jayla and John are saying in the chat. And right, okay. So here we go. So let me go back to finish this. But yes, the big basically to Jayla and John, the big answer is yes. And well, definitely everything I'm doing here is totally exactly the same thing as was in homework 2. We just hadn't gotten to it yet, talking about it in class homework 2. But yes, this is exactly where we left off in homework 2 was how to deal with these E's and these I's. Now look, I'm just about to, so back to it. I say, but I'm very proud. I mean, I'm very happy with what John and Jayla and and Lizzie and other people are putting in the chat. Like, I think you are totally really following this. Because look, we say, okay, all that business there, that whole x naught e to the blah, 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 is x. And then we go, I squared. Like, what's the deal with I squared? What's the deal with that? Well, remember, I equals the square root of -1. Thus, I squared must equal -1, right? If I equals the square root of -1, then I squared equals -1. So, wow, what just happened? Oh, sorry. Okay, that was scary. So what I'm saying here, right, no, so totally, first of all, Jayla's thing, not only correct what Jayla is saying in the chat. Now I feel like I'm mispronouncing the word chat. Sorry. Not only is she totally right what she's putting in chat, but it totally is the point that I squared is -1. So when I got squared from the chain rule, it became -1. So there's our negative sign here. So in fact, what this shows is this just like cosines are a solution to our differential equation, and just like modified cosines or sines are, just like you can write a cosine as a solution, or you can write a cosine in a funny way, like cosine with a phase constant, or you could write that in a funny way and write it as a sine, but they all mean the same thing in the end. Apparently, if we do an exponent, no, I is constant. Wait, okay, the second derivative I becomes -1. Okay, so all of you in the chat are really good. What I'm saying is, in the second derivative, I becomes -1. I is the square root of -1. So when the chain rule brings out the I the second time, when we do, I am literally saying, yes, I squared equals -1. I still think that means that I is still a constant, but when you square that constant, you get a constant called -1. So I think this solution actually works. Like we are literally getting, remember the original differential equation, what that we were asking about was this thing written right here. Wait, I've got 14 minutes. You'll know that you don't worry if you're, I think you're getting it, and I appreciate the class participation like very much, believe me, very much. I think you're getting it, but if you, and I'm going to answer specifically a couple more things in the chat, but if you think you're getting it, but you're not entirely sure, don't worry. We're going to do one more quick practice. We have 13 minutes. We're going to do one more practice, which is the one underneath it. And you'll see the difference. So, and you can keep practicing in the homework too. Yes, this is just meant to be identical to what's in homework too. Yeah. So going backwards in the chat, John Board's saying, yes, I triple equal sign equals square root of -1. Yes, totally. So it is a constant. Then, yeah. So Jayla is rocking the Casbah here. Yeah. It's like the number 4/2, which that is 2, but it's still a constant. Right. Like, oh, I see what you're saying. Yeah. And also, it's also, guys, it's also just like omega equals the square root of k/m. Then you square that and you get omega squared or k/m, but that's still a constant. Like we're not saying that you can't do things to constants. And when you do things to constants, you get other constants. Like square root of k/m is a constant. Square it and you get this other thing, k/m, but that's still a constant is the point. And the point here is that once you squared I, you get the constant of -1. And that's what we needed. That was if I was just hanging around, if we still had I in our final answer, then this wouldn't be an answer. It wouldn't work. But we wanted, in other words, it's not the constant that we wanted in our final answer. The final answer that we wanted was -1, but I got squared because of second derivative, because of chain rules. So it worked. It's like how pi. Yeah. It is like how pi is always a certain constant. Oh, and you're raising your hand. And there's still one more question in the chat that I really want to answer, or at least two. Stephanie's, no, it's great that Stephanie, so for the second derivative, but I see John's hand, so hang on one second. Sorry, 409, wait, so the second derivative, I always becomes one. Well, hopefully I've answered. And again, all of you, please submit these things for points for participation, and they mean a lot to me, especially as we're getting close to an exam. It helps me to know that you're getting it. So as long as I did answer Stephanie's question, oh, it was a mistake. Okay. And maybe Stephanie wants to let me know either publicly or privately. Like I would say, because I'm glad you're asking, Stephanie. So for the second derivative, I always becomes 1. I did. Okay, cool, fine. Now there's one last, I want to do one more exercise here with 11 minutes left. But when we say, okay, let me just, on John's thing, because this is good. So relating back to homework 2, because this is what John's asking. If you had something like this, yeah, if you have x equals e to the I omega t, or he wrote omega I t, but same thing, then dx dt would equal I omega e. This is back to homework 2. And if I did a second derivative, it would be what this is all showing. Right. Oh, perfect, Stephanie. Now you, right. Well, if it was like I to the fourth, it would be 1, not negative, correct. And if it's I to the 3, all right, so look, I'm going to say this quickly to everybody. This is great. And Stephanie, you're rocking the Casbah, and Jayla rocking the Casbah. For real. Okay. You might be wondering, like, where the heck, like, why did I come into this? Because remember, we're looking for functions that get us back to themselves, at least eventually, or sort of, or with a negative sign or whatever, right? E to the x always gets right back to itself. The derivative of e to the x is e to the x. So, right. Very good, John. Right. And it's why these functions are useful or work for describing things that are, yeah, that might be a little bit of a stretch, but okay. Oh, actually, all right, I'll take it. Yeah, that's cool. Right. I'm just saying for the moment that where I actually bears a relationship to sine and cosine that we never might have thought about before is that in 4 steps, it gets back to itself. It oscillates back to, it does a full period. Yeah, I mean, I really do like what John's saying in the chat there. And so apparently, if you put i's and e's together in a certain way, you'll produce the same effect as you produce with sines and cosines. Now, the I has to be there. The I has to be there to do this magic that it's doing with the negative signs. Like, we are saying e to the I omega t is equivalent to cosine of omega t. I mean, that's the thing that is coming, that we're realizing here. But we need the I very quickly. I know I have 4 minutes left. Like, in other words, in order to describe oscillations with an e function, you need the I as well. E is not equivalent to cosines by itself. An exponential function does not oscillate by itself. because the negative signs don't work. You could see that in the very next example. I'll do very quickly if I can, very quickly. Oh, in fact, I have it here. Sorry. If you go back. So these pages are a little bit out of order, but if you go to B1, 2, later on in the page, then it says, is this a simple harmonic oscillator? X equals X naught E to the blah. And notice there's no I that time. Now, one quick question too, especially since one quick comment, since we only have 3 minutes. There's an error on this page. Let me screen share again. Please correct on your page. I'll try to issue an update, but so I'm here on the page. Yeeks. I'm now looking at the very bottom thing. In 3 minutes, I just want to finish this part B at the bottom of this page. But so it's asking now, is this thing a harmonic oscillator? It's like the identical expression to what we just did, only it doesn't have the I in it. So it's actually easier. But I'll tell you right now, it's going to get a different answer. I'll tell you 2 things right now. Number 1, the answer is going to be no. It does not satisfy the differential equation. Okay, for this very last one, for B1, I don't know if I can annotate, but I'm talking about this. Okay, I'm talking about this business right here. This is where I am. And the answer is going to be no, it does not satisfy. And I'll show you that in a second if we don't run out of time. But if you take 2 derivatives of this, you will get back the X. It'll look all good and everything. It'll look perfect, but it won't have that negative sign in it because there's no I being squared giving you that negative sign. The negative sign will go away here. And so this is kind of like on Stephanie's question. The negative sign won't work without the I. So this thing is not a harmonic oscillator. It won't satisfy the differential equation. And one thing, there's an error where I'm saying there's an error right here. It says, does this cosine expression? That's an error. It should just say, does this expression? Okay, it's not a cosine expression. It's just an expression. That's an error. Please make a note of that. But if I have 1 minute left, if you want to see, or if you want to hang out for 1 minute after class, you could see, or you could practice on your own. But when I go to take the derivatives right here, oh, I'll switch the board. Oh, God. Okay, yeah. And of course I'm gonna upload these notes. I'm gonna post these notes in the Google Classroom anyway, but just so you can see right here, if you take the 2 derivatives, that whole KQ over R squared thing will come out. And the first time it comes out, it will come out with a negative sign, but then it'll come out again with a negative sign. The negative will multiply by a negative and get a positive, and that's it. And then we get a positive. This is the last thing we're saying. It's 420. But so this one won't work, thereby showing if you want, you can express oscillators with exponential functions. You can find other solutions to the differential equation. They can even be exponential. And exponential functions, if you're aware of it, they usually go up or they decay down. They're monotonic. They don't look like oscillators. But they can be used to capture oscillation as long as we throw in the I. But if we don't, then they don't work. That's the conclusion of this. That's class. You guys have been very, very patient. I was going to give you time to work today on your own. I'm sorry I didn't, but maybe this was more productive. I don't know. But I'll post the video. I'll post the notes. We'll keep talking about this next week. I really appreciate, and I'll learn how to pronounce all your names, but I really appreciate this class. You guys really rock. You can. Oh, good. Oh, thank you. How nice. Well, thank you for saying so. Thank you. But your questions were great. So all of you, thank you for saying so. Okay, so have a good weekend. I'm going to shut up somehow. Oh, your name. Oh, your name was written. Wait. Thank you. Oh, I don't even think. Well, I'm not saying it's spelled badly. That's not my. Oh my God. But have a nice day. Yes, I think it's spelled. I don't even. Oh my God. No, I think it's spelled great. I think it's a great name. No, thank you. Thank you. Oh my God, I'm so over. It's just, I'll have to explain this whole thing later. Okay, but it really is true. All right, fine. No, I believe you now. Now there's a good story. But thank you. Have a nice day, man. Thank you. Oh, good. Oh, good, good. Oh, cool. How nice of you, Elizabeth. This is such a nice class. I'm gonna cry. After I hurt myself. Cool. Oh, I should also stop the